Good morning, students. Next topic is aryl halides. In aryl halides, these are aromatic halogen compounds in which halogen is directly attached to an aromatic ring. For example, chlorine that is directly attached to benzene ring, bromine or iodine. These are directly attached to benzene ring. These are called aromatic halogen compounds. There may be possibility that halide that will be attached to the side chain of side chain of the alkyl group. In that case, for example, if we take toluene in which one hydrogen is replaced by the chlorine atom, that is called benzyl chloride, and that are called alkyl halides. These are not aryl halides. Aryl halides are only which are directly attached to the benzene ring. But alkyl halides in which side chain is replaced by the halogen group, that are called alkyl halides. Next is methods of preparation. First method is nuclear halogenation. In nuclear halogenation, there will be direct halogenation of the benzene ring, and in this, as aromatic ring, direct chlorination or bromination of aromatic ring that takes place at low temperature or in the absence of sunlight or in the presence of Lewis acids. मेनली इसके लिए क्या ज़रूरी है कि या तो लो टेम्परेचर होना चाहिए या अपने पास सनलाइट की एब्सेंस में या अपने पास लुइस एसिड्स की प्रेजेंस में, और मेनली लुइस एसिड्स की प्रेजेंस में फॉर एग्जांपल फेरिक क्लोराइड FeCl3, aluminum halides which act as catalyst. So in presence of catalyst there will be direct halogenation of benzene ring. In this we do not directly add reaction mixture some iron fillings, and that will react with the halides, and there will be formation of ferric chloride in situ. It means in reaction mixture it will be prepared automatically if we add some iron fillings into the reaction mixture, and there will be formation of ferric chloride that act as catalyst. So benzene plus Cl2 in presence of Lewis acid FeCl3, there will be formation of chlorobenzene, direct halogenation. And if we use normal concentration of Cl2, then reaction will stop at the mono substitution stage. And if halogen is taken in excess amount, for example Cl2 in excess in presence of catalyst FeCl3, then there will be formation of isomers, that is will be next Cl will be attached to ortho position or para position, then it will form ortho and para dichlorobenzene. Similarly, if we add, in spite of taking a simple benzene, if we take toluene, that is substituted benzene, plus Br2 in presence of FeBr3, then there will be formation of ortho and para product, and this takes place very easily as compared to chlorine because it will be substituted benzene ring. Now there will be, so in this method there is only one thing, that is we use catalyst FeCl3 and direct halogenation. If we use excess amount of halogen, then we obtain substituted products, it means ortho or para, mixture of ortho and para products. Next is limitations of nuclear halogenation. In limitations, first limitation is direct halogenation, that as we see there will be mixture of ortho and para products, so there will be mixture of isomeric aryl halides, so which cannot be easily separated. And if we want to specific orientation, that is meta product with respect to particular, then we cannot obtain meta bromotoluene, cannot be prepared by direct bromination of toluene. So first is mixture of substituted products, या mixture of isomeric aryl halides we obtain. Second is if specific orientation meta product, that will be not formed. Third is if we use aryl iodide, then we have to use, if we add I2, then we have to add oxidizing agent, because oxidizing agent like nitric acid, mercuric oxide, and that will be a reversible reaction and oxidizing agent that will shift the reaction in the forward direction. Then in aryl halides there will be removal of I2. Then this will be a reversible process. So for reversible, to prevent the reversible process, then we have to add oxidizing agents. Next is aryl fluorides that are never prepared by this method because reaction with fluorine is very violent reaction. So all these are the limitations of nuclear halogenation. Next method is from diazonium salts. An important reaction is Sandmeyer reaction. In Sandmeyer reaction, that is diazonium salt, firstly how will you prepare diazonium salts? We use sodium nitrite NaNO2 plus HCl. Then there will be formation of HNO2 plus NaCl. Then with aniline, aromatic amine, aniline plus HNO2 plus HCl at low temperature 273 to 278 Kelvin, then there will be formation of diazonium chloride. So this is the method of preparation of diazonium salts. So first अपन reaction कर रहे हैं next second reaction, that is Sandmeyer reaction, in which benzene diazonium chloride that is reacted with copper chloride, that is cuprous chloride in HCl. Then there will be removal of N2 and formation of chlorobenzene. So it is the halogen, that is chlorine, that will be obtained from copper powder, copper chloride, cuprous chloride. And if we have to obtain bromobenzene, then we will add copper bromide, cuprous bromide in HBr. Then we obtain bromobenzene plus N2. So in this halogen that is attached to the benzene, that comes from cuprous halide. Next is important reaction you have read already in +2, that is the Gattermann reaction. Gattermann's reaction, in spite of using cuprous chloride, we use copper powder and HCl or HBr. Then we obtain bromobenzene plus removal of N2 plus removal of HCl. Then next is preparation of ido compounds. In ido compounds, simply we add Ki, aqueous Ki, that is potassium iodide. Then there will be formation of idobenzene, and this is the very simple method by warming the diazonium salt solution with aqueous Ki. Next we can obtain fluoroarenes, that is Burl-Schiemann reaction, that is also important reaction. In this, firstly we prepare benzene diazonium tetrafluoroborate. In this, aniline is reacted with same NaNO2 plus, in spite of using HCl, we use HbF4. So at 273 to 278 Kelvin, so we obtain N2 positive, BF4 negative, that will be benzene diazonium tetrafluoroborate. Then we heat and there will be rearrangement and removal of N2, and there will be formation of fluorobenzene plus BF3 plus N2. So this will be the formation of fluorobenzene. So that's important reaction, Burl-Schiemann reaction. And in alkyl halides, as we read that we can substitute alcohols, for example OH group, that is easily substituted by the Cl group. Then in this aryl halides, that cannot be prepared from phenols because OH hydroxy group from benzene that not be easily substituted, and so we do not use this method as we use in alkyl halides. Next, third method is from organothallium compounds. Organothallium compounds, we use thallium trifluoroacetate. What is the formula of thallium trifluoroacetate? Trifluoroacetate, acetate group is CH3COH, CH3COH, and trifluoro, all the hydrogen atoms are replaced by the fluorine, then it becomes CF3COH, that is trifluoroacetic acid. And if we use acetate group, then H group is removed, so it becomes CF3CO negative, as thallium having 3 positive, so CF3CO group will be 3 attached to the thallium group. In presence of trifluoroacetic acid, Then firstly in aryl group, yeah, benzene group, hydrogen is replaced by the thallium group, and then ar thallium, two groups are attached, the one removal of cf3 coh, and finally we add ki in presence of water, and when we obtain the idobenzene plus removal of cf3 coh. And the most important aspect of this reaction, that is we obtain the products in specific manner, specific position. For example, if we take already see bulky group on the benzene ring and we add trifluoroacetate, thallium trifluoroacetate in presence of trifluoroacetic acid, then there will be addition of the thallium group at the para position, because already bulky group is present on the benzene ring. Next we add again Ki, and there will be formation of para product with respect to the bulky group already present on the benzene ring. And if we add at high temperature, then above reaction leads to formation of meta products. So all these are the methods of preparation of aryl halides. Next is physical properties. Physical properties, first physical state, these are colorless oily liquids or crystalline solids. Second is density and solubility, they are heavier than water and less soluble in water and more soluble in organic solvents. And as we have to separate ortho and para isomers, so para isomer that will be less soluble in a given solvent than the ortho isomer, for the purpose of separation of ortho and para isomers. Third property is melting and boiling points. Melting and boiling points of haloarenes, that is same as alkyl halides, containing the same number of carbon atoms. And if we compare the according to the halogen groups, then ido will be more melting boiling point than bromo, then chloro, then fluoro, because as there will be increase in the size of the atom, then there will be more van der Waals forces of interaction and more will be melting point and boiling point. Third point is, if we take the size of the aryl group, as the size of aryl group increases, then melting and boiling point also increases. That same reason, because of increase in van der Waals forces of interaction. Next, if we compare ortho, meta and para isomers, then then para isomer that is having high melting point, because जो para isomer that is very symmetrical and fits better in the crystal lattice, so it is difficult to break the crystal lattice and we require more energy to break the crystal lattice. So para isomer has very high melting point. Thank you, students.